So, thank you. Welcome. I'm JD, as she mentioned. I'm one of the founders of Pachyderm, the other being Joey, who's in the audience as well. And we're both former RethinkDB guys. I was one of the early employees at RethinkDB. So I can't answer some of your questions about that, but I'm definitely not the most informed about that in this audience now, given the entire stuff. So what we're going to be doing today is a neat integration between RethinkDB, which I'm sure you all know about, and Pachyderm, which you probably don't all know about because it's a very new product. But the short pitch of this is that Pachyderm is MapReduce without Hadoop. It's a completely new MapReduce platform that leverages Docker to create MapReduce jobs rather than Java. We can talk lots about that, but the part that we're going to be using today is the distributed file system. And the distributed file system, which is sort of the analog of HDFS, is really cool because it has git-like semantics. And it does this using copy on write, which it borrows from BetterFS. And so what we're going to do today is we're going to take RethinkDB instances and have them push their data into Pachyderm so that we can get these git-like semantics for our database's history. And we can see like our database's data set as it evolves over time and play with that. So first off, let's look at the tools on hand. We have RethinkDB, which of course you're familiar with, and these tools each have like different strengths that we want to capture. RethinkDB is really, really good for real-time stuff. You put a bunch of data in there and you can like get notified as it changes. You can quickly access it. You can quickly do analytical queries. It doesn't have a notion of history. The data that's in there is the data that's in there. You don't know what it was in the past. And as soon as you overwrite a piece of data, you don't know what value you've overwritten. And it also isn't built for like true large-scale batched analytics. So like you can do, you know, basic MapReduce stuff, but if you wanted to like do a machine learning model, that would probably get a little bit hairy and requel. Pachyderm, on the other hand, is a MapReduce engine. It's not built for real-time access, but it does have this git-like file system, and that means it does have a notion of history. And it is designed for batched analytics, although that's in an upcoming release. We don't have that yet. Okay, so what do we need to do to combine these two? What do we need to do to get the best of both worlds? So the basic layout for how we're going to do this, first. Why would we want to do this? So the reasons that we want to do this is so that we can do these heavier weight batch analytics on our RethinkDB data. Also, this allows us to have some degree of disaster recovery. You know, if you have like a per minute snapshot history of your entire database's history, there's a whole set of cases that you just like can't run into. You can never be in the case where you're like, how did this data get to be like this? Why is it in this corrupted case? And this can also be useful for migration because PFS can let you send this commit history from data center to data center and do migrations like that and maintain that history. So how do we implement this? So the basic steps of this are first, we need to have some way to take data that's in RethinkDB and push that out into PFS. Then we need to have some notion of what do our snapshots look like. How often are we committing? Are we committing every day? Are we committing every minute? And obviously, with anything like this, you always want higher granularity because it lets you do more, it lets you see more detail, but that also comes at some sort of an overhead. So we can take a look at what that overhead actually is. And then lastly, how do we actually use this saved data once we've got it? So those are the basic steps that I'm going to go over. First off, any questions on the approach? No? On the same page? Okay. So step one, dumping data to PFS. This is fortunately really, really easy because RethinkDB has an HTTP command. And I've heard people at RethinkDB say how like HTTP is basically like 50% for demos, which is honestly like a pretty good reason to have a feature. But it's actually great for this stuff too because it lets you just interoperate with any other product that has an HTTP protocol. So this right here is a requel query. It's in Python because I find that one to be the best looking language to write requel in, but you can translate it to anything else. And I'm just going to walk you through what exactly this query is doing. So first off, you see r.http at front. And if I put my mouse over something, do you guys see it? Okay, so you see r.http right here. That's just the requel HTTP command. And then the first argument to this command, and actually the only required argument, is the URL that you actually want to send this request to. So here we've used host in angle brackets. And throughout this talk, when we have something in angle brackets, that means the name of something that has type whatever's in there. So this, in this case, this is the machine on which PFS is actually running. The next part of the URL is the word file. And this is a PFS-specific keyword. And what we're telling PFS with the word file is that the object that we're creating here, the object that we're giving you, is a file. Put this into the file system. And in a few slides, we'll see we'll manipulate some objects that aren't files. And you'll start to sort of understand the ontology that we have going there. And then the last thing is the name of the file that we want to create. And in this case, I'm assuming that this is a table that has ID as its primary key field. And the reason that I use ID, and this is actually an important detail, is because that's the only thing in the document that's actually guaranteed to be unique. And I want to make sure that these files in the file system actually are all unique so that they don't clobber each other, because if they do, I'd lose data. So that's what we're sending this request to. Then you can see the method we're using. The HTTP method is a put. And if that should make perfect sense because we're putting a file into the file system. And lastly, we need to pass the actual data for the doc. Which comma? Oh, yes, that is a typo. Sorry, that should be. No, that is completely a typo. We want to like add these two strings together and concatenate them. Okay, so yes. So the simple answer is that RethinkDB is, this would be a slightly longer query if I did a post, because when you do a post and you pass something to data, it interprets that as form parameters, and like will give you a completely different HTTP request. So when you do a put, it serializes this doc value to JSON, and that is the value you send. It also sort of in the HTTP nomenclature makes a little more sense for this to be a put, because you're like directly creating an object rather than something, and this is indeed an idempotent command. Any other questions? Is everyone good? Okay, so that's namespacing. We'll get to that. So this is how we push one document, right? Now let's scale this up to pushing an entire table. Fortunately, RethinkDB has really nice commands for that too. They have a for each, which will let you run a write query over every value in a table. So we expand our put query to do the entire table. Now this looks mostly the same, but you'll notice a few changes. First off, at the top, we're putting this inside of a table.forEach. That's so that it runs this on every single row in the table. Secondly, you've noticed we've added namespacing. This is to what Robert brought up. Basically, this is creating a directory for this specific table that's going to hold all of the data that we're creating. And then the last thing is we've got this little bit of annoyance at the bottom where we've had to chain a .do onto it. And that's just because for each actually expects every single expression that it evaluates inside of it to result in an object that looks like this. And RethinkDB will actually yell at you if you don't put this .do there. Questions on that, or we're good? So PFS doesn't have a notion of a table. It just has a notion of directories. And PFS treats directories basically the same way that Git does, which is just that a directory exists if files in that directory exist. But there's no independent notion of a directory. Okay, so now we can dump an entire table. But that's still not quite what we want. What we really want is we want to have a table that just gets synchronized all the time. And now is when we can bring in the nice sort of new RethinkDB feature of changes, right? And what change feeds do, for those of you who aren't familiar, is they let us run a function over values in a table as they change. So anytime a new value is inserted into the table, our function will get called back and we can do something with it. In this case, we can push it over to PFS. And so now the query's evolved a little bit more. First off, we've put a .changes here in between our for each and our table. And then we've also added a bracket operator in there to pull out new val. And that's just because when you get a result in a changes operation, you get an object with these two different values, the old val and the new val. We actually don't care about the old value at all. That's actually already stored in PFS and what will sort of get overwritten when we send in the new val. So we can just focus on those. Any questions on the changes? That one follows pretty. Okay, so that's step one. We now have a table in RethinkDB that's having all of its changes pushed over to PFS. The next thing that we need to do is we need to schedule commits so that we have some sort of granularity for these changes. This right here, this is not a RethinkDB command. This is something that you would put in your cron tab, just to make sure everybody's on the same page. And this is a PFS command to create a commit. So first off, these 5 stars at the beginning, that's just the way of telling cron to do something every single minute. The command that I'm having it do every single minute is a curl, which most of you are probably familiar with, but for those who aren't, I'll just go over exactly what this means. -xpost means that the method I want to do is a post, and the route that I'm posting to is, again, my PFS host, but now the keyword is commit instead of file. And that's because the thing that I'm creating here is a new commit, which is like a snapshot of the data. It's completely isomorphic to what a commit is in Git. In particular, it's also about as cheap as a commit is in Git. This is actually like a very, very fast constant time operation, because all that it's actually doing is allocating a new empty node in a B tree and referencing the old B tree in a copy on write fashion. This is something that is like incredibly interesting we could talk about on end, and it's also something that is in all of the white papers on Btrfs and is very interesting to read about. And I will certainly happy to do my best to answer your questions on it at the end, but I'm far from expert. So any questions on what this command actually means? Yeah. Yes. So this will return a UUID, which corresponds to the commit. And then you can also get a list of those commits with timestamps using another command. Yes. This is PFS. This is what PFS actually does and what the file system actually does, is it will commit all of this and give you a way to reference all of that later. So what have we created so far? This is the picture of what we have. We have RethinkDB. Every single minute we take a snapshot of what's in RethinkDB and we record that in PFS. And so we get these layers of commits that represent the state of our database and that we can use later. Any questions on the overall system? Yes. Mm-hmm. It's really, really fast. Yeah. And that's, I mean, I wish I could take credit for the brilliance of that, but that's really all BetterFS. You know, it's fast because the thing we have to call is fast. Yeah, I mean, if you get, you know, if you have cross-cluster latencies and you have net splits and stuff, like, that's always expensive to resolve. But, you know, under normal operating situations where you're not solving those problems, it's actually quite fast, yeah. So what happens when you send that commit is it goes to a particular node that will route that out to various shards in a consistent way. And so it's the BetterFS equivalent of this command will get run on every single box. It sort of depends on how you think of it if you want to say that commit is getting run on every box. It's fair to say that commit is getting run on every box. No. So Btrfs is completely uncluster aware. PFS can really, you can really think of it as the distributed layer on top of Btrfs. Yes? Yes, absolutely. All right, so the first part of that question was, can I repeat the questions, which is what I'm doing right now. The second part of that question was, surely that must take longer at some time. I mean, the answer is that my experience with it so far and my understanding of it algorithmically is that it actually is really hard for this command to stall because it is allocating the same amount of very small disk space every single time. Of course, at some point this will stall if you have like a machine failure or something. And the way that you deal with something like that is you have multiple replicas. And so you would have like 3 concurrent replicas of the file system. And you would say like, okay, only 2 commits need to actually complete for this to count as complete. And then you sidestep that like 1% case. Doing quite well. Yes? Mm-hmm. So it's not adding something into a B tree. Repeat the question. I always forget to do that. So the question is, I said that it was constant time, and then I said it's getting added into a B tree, and that's logarithmic. And this would suggest that I am lying. And everything you said there is quite correct. So what is actually going on is when you create a commit, that isn't inserting something into a B tree. What it is doing, it is allocating a new completely empty B tree node and referencing the one before as the parent of it. And the way that BetterFS actually works is when it looks for a file, it knows to sort of look in the brute B tree first and then like cascade back into the other ones. And adds in a couple of optimizations on this so that it knows where to find things. So the process of committing is actually quite fast. You could occasionally wind up paying some costs on accessing. I haven't done a huge amount of research on when those start to become a problem. I haven't observed them. I've done, pretty decent sized tests now, and I haven't observed them to start to become the problem. But, I'm sure in any piece of software you're going to hit things like these, and then you're going to have to figure out how to sidestep them, and that's the fun part. Anyone else? Okay. So now we get to go on to the cool part, which is now that we've got all of this stuff in PFS, how do I actually get this back into RethinkDB? And so long-term, PFS is going to have a whole MapReduce engine that you could do all sorts of cool analytical stuff on this, but it's still a cool use case to restore it to your database, and that's what's actually working today. So we're going to go over a few more PFS commands to get data out of the database, and then I'm going to show you how to chain those back into RethinkDB. So first off, and this is exactly what I promised to Slava, this is the way to get my commits after they've been made, if I don't happen to have written down the idea of them. It's just a simple curl command where I do a get to host/commit, and this time I'm not posting anything, so it doesn't create, it reads. And this will just give you a list of commits going back in time with the commit ID and the timestamp. And the idea of this is you pass this into grep to find the commit that you're interested in. If you wanted to get back to January or something, you would grep for January and see one on January 1st. And then armed with a commit, you can get a dump of the entire table at that point. Yes?
Sorry, just a quick question. So when you do a curl with a what's the format that it returns the information? Is it like a JSON document?
No, so it's actually just lines. It's actually like sort of what, it's in fact very similar to what you'll get if you type git log, except we don't have a notion of commit messages yet, but we will eventually. And it's designed to be passed to all your standard Unix tools. Yes?
If you create all these commits, do you eventually have to do some sort of garbage collection or like
Forgot that question. Yes, repeating the question. If you create all of these commits, do you eventually need to do some sort of garbage collection? The answer is yes, absolutely. Like there are many scenarios when you're going to need to do garbage collection, and that's actually quite easy to do, and BetterFS makes it really easy to do. You can basically just delete a commit, and BetterFS is smart enough to figure out how to keep track of all of the things that are on the commits to the side and only lose the things that were specific to that commit. Yes? So the question is, why did I use BetterFS rather than ZFS? I actually like ZFS better, or I call it ZFS. I think that it just sort of has its features are a little bit more fleshed out and a little more usable. I chose BetterFS because A, it's actually in the Linux kernel, which makes it a lot easier to deploy, and B, it's what Docker uses. And because Docker is such a core part of that system, that means that that's sort of a dependency that we completely get to sidestep, because a dependency on Docker means a dependency on BetterFS means we're only adding one dependency. That being said, I very much designed this with the ability to use multiple backends in mind, and am very interested in long-term being able to support all of these, because they have such an equivalent feature set. It's not too hard to write generic code for all of them. But BetterFS just seemed like the best non-moving target to pick right now for a first run, is the simple answer. Okay, so we have our commit now. And Now we want to get the data out of it for this commit. And so we do another curl, and this one's also a get because we're getting things. Host, you're all very familiar with by now. We're back to the file route because the types of objects that we're manipulating are files. Table was the name of the table that we dumped it to. And now we're using a star. And the star is a special purpose operator in PFS. You can't have a file called star because that would really, really confuse you and break a bunch of commands. And it behaves exactly like star behaves in shells. When I have a star at some point in a path, that means that it matches any possible name in that path. So when I execute this, this will get me all of the files that I put into that directory. And now I append this query parameter to the end with the commit that I got from my previous thing. Oh dear. And what this does is it gets me that directory in the file system as it was at that commit, right? And so this allows me to see things at all the way back in time. And now once I've got this, it's a very, very simple command to actually pipe this back into RethinkDB for analysis. And so this command is, first off, the part on the top is identical to what I had above, but I'm piping this to RethinkDB import, which takes a stream of JSON and puts it into the database. And I'll just walk you through this command, although you're probably mostly familiar with it. RethinkDB import is utility for that. It takes a flag parameter of a file. We had to do a little hack here to get it to read from standard in, because it doesn't actually have a way to do that, but perfectly free to pass standard in as that file it reads from, and it's none the wiser. And then lastly, we need to give it a name of the table that we're creating. And this is something that's worth noting because we're going to be referencing this name a lot. We've called the table at commit. You could probably give this something more meaningful when you're restoring like table in January or table in, I don't know, Q1, whatever. But once you've run this command, your RethinkDB instance will actually have a table called that looks like what your table looked like when that commit was made. And lastly, you don't even have to do this to the same RethinkDB instance. And that can be really nice as well, because oftentimes you want to like boot up a historical commit and do some analytical stuff on it, and you don't want to tax your production database. You don't want to risk taking down your site with stuff like that, because obviously you never want to do that. Yes? All right, so there are two questions. One, are the results ordered? The answer to that is no. They are not ordered right now. What they are ordered by is the order that BetterFS sort of inserts them into the B tree and puts them on disk. So they're ordered to optimize for how quickly you can read them off of disk. There'll probably eventually be a way to get them out ordered, because like that's a feature people are definitely going to ask for, but we don't have it yet. And what was the other question? I'm sorry. Oh, the other question is, can you do ... in paths? No, we don't have, if you could do like star / ... star, like star a bunch of different things, yeah, that would be, like you have a Turing complete path system pretty quickly. No, nothing like that, only stars. Ordered, like, are they ordered by primary key, I think, or by an arbitrary thing, which would be even more interesting, but even harder. No, these are completely ordered to optimize for how quickly they can be ripped off of disk. So you cannot, there's no way to get them out ordered right now in PFS. It's an interesting question what that's going to look like, and it's something that we're definitely going to need to have, because very often in a MapReduce job, you want to have ordered results that stream in. So doing that efficiently, being able to basically do a like distributed merge sort, that's something that we're definitely going to need to have. Yes? Yes, the question is, can you not just pipe it to sort? You of course can. This just gives you back a stream of files, so you can change it to any Unixy operation. I don't know exactly what the scalability on sort is. I would assume is storing everything in memory, unless it's doing something smart with like a device map file or something. So depending on how much data you're storing in PFS, PFS is definitely designed to be able to store an amount of data that would seriously crash sort. No, but I mean, in programming, so often the ideas that aren't good ideas are the good ideas. Okay, any other questions? So we've restored our table. And now we can do something really, really cool, which is that we can query historical data. So if I take some table.map.reduce, that's some command that I'm used to running over my table, and I run it instead over table at commit, then I get a result in RethinkDB that looks like what would have happened if I'd run this on a table, the table a year ago. And so this can be cool if, like, the best example we had when prepping for this talk was like for doing historical scoreboards. And you come up for some way of like scoring your users, and then you want to see like what was this scoreboard like a year ago? Like how would this metric have evolved? Another very, very cool thing that you can do is you can kind of pivot this. So rather than getting out all of the values for a table at a specific commit, you get out all of the values for a particular document across all of the commits. And so you would basically wind up with a table that shows how a single row has evolved. And this can have a ton of use cases. Like one obvious one is you've got a user's row is in some sort of a bad state, and you want to debug this and figure out how it got to there. You can do that. This is also, you can like show timelines for your users and stuff. Although, if you had to do like a restore for every single user, that gets to be a little bit unwieldy. So doing that better, interesting. There is one thing you can't do, however. Any guesses as to what that is? Yes? Sorry. So yes, that is one major flaw, you're right. And you would, to do that, that's actually not too hard to do. You sort of, so the question is, if you delete something from your database, does that get accurately reflected in PFS? The answer is no, within what we've done in this talk. It's actually quite easy to do that. You would just sort of need to dive into the old values. And to be honest, it seemed like it sort of would have been a detail that maybe detracted from the talk a little bit. But just because we would have had to go off on a tangent for a while. But yes, that is the answer, and that is something that it does not do right now in this demo. But that isn't the problem that I'm talking about. The problem that I'm talking about is we've now got this table, table at commit, that represents how our table was a while ago. We can do all sorts of read queries on this table, but write queries don't really do anything. I mean, we can modify it still in RethinkDB, but this doesn't get pushed back into PFS in any meaningful way, which is honestly could be fine in a lot of cases, but so if this table at commit, this is now sort of a dangling table in that like we have this change feed operation out on our original table that's constantly syncing it, but we're not doing that on our new table. And if we wanted to just start doing that the same way we did with the other one, there'd be this huge upfront cost because we'd have to like resync all of this data. A reason that this might be useful is some of the people we've talked to have sort of been in a situation where they want to do like a migration of their site. Oh, so the problem here is basically that we don't have synchronization set up. We're not snapshotting table at commit, right? It represents a single snapshot in time, but if we want to start like writing to an old snapshot and branch out, there's no way to do that. Right. Basically, we want branching. And it so happens that that's a feature we did in our last release. In 0.2 of PFS, and I'll show you how that works as well. So first off, we need to know how to create branches, and this is now something that you're well familiar with. This is a curl command. We're doing a post. We're doing it to PFS. New keyword, though. This time we're creating branches, not files or commits. And creating a branch takes two arguments. It takes the commit that you want to branch off of, and it takes what the name of this new branch will be. And this concept of branching is designed to be completely isomorphic to Git and to feel exactly like that. So when you create a branch off of a commit, this gives you a new active thing that you can write to and you can create commits from. So once we have our branch, we need to set up the synchronization to this, and you can see this command is almost identical to what we had before, except we're doing it to a different table, and we've applied this extra parameter at the end, where we specify that we don't want to push this to the default branch, which is called master, to borrow the analog from Git. We want to push it to a new branch that we've created. And then, of course, we need to schedule our committing again. And with these two commands, we now have a branched copy of our table that we can modify at will, and it'll still get synchronized, and it'll still get committed, and we can roll back those changes too. And so this is the picture of what we have now. Any questions on that? That's all of the technical content that we have for what you can do with RethinkDB and PFS. I'd love to answer any questions. Yes. So the question is, can you do other git-like things with PFS, such as tag and merge stuff? This is basically all of the git-like features we have now. Long-term tagging doesn't seem too hard and is definitely an option. One of the biggest discussions we've had is what exactly merging is going to look like, because merging doesn't translate particularly well from stuff at the human code scale, like the size of a human repository of information, up to like a data center size. Because a merge conflict is over terabytes of data, and you certainly can't resolve that by hand like you do in Git. And so basically, to merge, you're going to need some notion of like a MapReduce job that does that. So we're going to need to figure out exactly what the use cases for that are and exactly how to do that. One of the things that is not fully exposed yet, but is mostly implemented in PFS is very interesting, is pulling. And that's really, really cool because for one thing, it lets you do efficient cross-data replication. And it lets you, pull a data set from one to another and maintain the whole commit history and everything like that. The other reason that pulling is really cool is because it gives you a kind of natural way to pull data sets locally. Now that sounds like something that is a really bad idea, because if I pull a terabyte data set locally or a petabyte data set locally, my machine obviously can't handle that. But PFS is going to eventually have the ability to sort of downsample these data sets. So you can pull locally, get like 1/100th of the data, do analysis on just that 1/100th, and when you like the analysis you've done, you push that up to the main cluster. Yes? In PFS, it has no notion of change feeds yet. Well, so the question is, can you subscribe to change notifications in PFS? It has no notion of change feeds yet. That is a feature that you mostly need to implement to do like a MapReduce pipeline, because a MapReduce pipeline is, in some senses, like the process of doing a MapReduce pipeline is take the changes, apply your mapping function to them, and then re-reduce it in. And so this is really just a question of exposing it. The BetterFS actually gives you everything you need to do to find all the new changes to a file system. It actually has this like wonderfully convenient call that you can make that will just show you all of the files that change from one snapshot to another. And it's just a question of exposing that. Questions? All right, well, our last thing is sort of the key takeaways from the talk and sort of some of the things that I found nice during this. The first one is that combining tools can be really powerful, and the key to doing that is interoperability. And in particular, that means having HTTP APIs. I have a very opinionated idea on what interoperability is. So hats off to RethinkDB for having an HTTP command. That just really wouldn't have been possible without that. The other one is that copy on write is just a really, really powerful, nice storage paradigm. When your data nodes can do copy on write and you can efficiently like store these snapshots, you can offer really, really cool features on a cluster scale. At least I find them to be very powerful, and I like the features that we can offer with them. And we would love to hear from all of you, both at RethinkDB and at Pachyderm. Yes, and Annie, this artwork is compliments of Annie, whose artwork you're all very familiar with, but she was nice enough to do one with some pachyderms and the RethinkDB mascot that we think is absolutely amazing.